Thank you for joining us. My name is Phillip Walsh from VUV Analytics. We build vacuum ultraviolet spectroscopy detectors for gas chromatography applications. I'm going to talk to you about some work we've been doing on implementing GC-VUV for analysis of fuel samples. We have about 45 minutes today, and my intention is to talk for about 35 minutes or so, and then to answer questions at the end. You have a little interface on the bottom left of your screen where you can type in questions. Our intention is to answer all of the questions even if we don't get to them today, so feel free to type in as many as you want, and we'll follow up one way or the other if they're not answered today. So we'll start with a screenshot of our VGA-100 and a schematic of our VGA-100 VUV spectroscopy detector. What we do is collect full wavelength range 115 to 240 nanometer absorbance each time we do a scan. And this scan can occur at a rate of anywhere from 2 scans a second all the way up to 100 scans. And a typical scan rate would be 5 to 10 scans a second. Now, the portion that we actually use depends on the application. So for the spectrum I'm going to show you today, and for these gasoline analysis, we typically use the 125 to 240 nanometer. The portion that's below about 200 nanometers, that's the part that you can think of as the vacuum ultraviolet region of the spectrum. Vacuum ultraviolet is a little bit of a misnomer because you don't actually have to operate in vacuum. What you do have to do is eliminate all the oxygen and water from the ambient, and we do that by maintaining an inert gas purge. So if you look at that schematic that's over on the bottom right there, our detector is sectioned into 3 main modules. Source module, which of course houses the lamp, and then there's a flow cell that connects the 2 modules. And then there's a detector module that has a grating and a CCD array detector. The flow cell is isolated from the other 2 modules by UV transparent windows. The inert gas, usually nitrogen, but we could use argon as well. That purge is continually going through the detector and the source module to maintain the environment there so that you can propagate vacuum ultraviolet light. Through the flow cell, of course, comes the eluent from the GC, which will include the carrier gas. Nicely for us, the common carrier gases, nitrogen, helium, and hydrogen, are all transparent, or at least largely transparent, to our detector. There's some of the few species that actually are. So that maintains, and to that we add a makeup gas that's usually nitrogen, but you can have other choices there as well. So that maintains throughout the entire system a VUV transparent optical path through which we can propagate the signal. And so the only time you actually see absorption is when analyte molecules come through the cell that actually absorb. Now, the nice thing about VUV absorption of gas molecules is that the absorption is typically very strong, and it's typically very distinctive of the different types of compounds. Over there on the bottom left, you can see kind of a schematic of the 2-dimensional output that we generate from our absorbance data. We do this by applying what we call spectral filters, but those are just regions over which we average or sum the absorbance. It's important to realize that no matter how we display or the response, even if it's on a 2-dimensional plot, this is inherently a 3-dimensional data set. So every single time point has with it associated a full wavelength range absorbance scan, like that ethanol that we're showing in this figure, and make use of that entire content of information when we do these gasoline analyses. Here's a screenshot of our VGA-100 controller screen. This is what you would see when the detector is being operated. The top plot is the sort of traditional chromatogram response. You've got time on the x-axis and response on the y-axis, and that's an integrated absorbance. At each of those time points, you have an absorbance from 125 to 240, like you see on the bottom graph. And that happens to be the absorbance of benzene. See on the top graph, there's a cursor at about 2.5 minutes, and that's the location that absorbance came from. So there are multiple plots on the top graph. Pointing tool here where I can show you how we get those. You could imagine that if I were to integrate from or to average the absorbance in this region that I've just outlined here, I'll capture the big part of the benzene response. And the reason I made that window a little bit large is that all aromatics respond with a maximum in their absorbance in that region. The location will vary a little bit, but if I do that averaging, the result is this light blue chromatogram that you see here. And that responds really well to aromatics, much more than it does to any of the other analytes. And so this gives you kind of a first order visual selectivity where you can go through and just sort of spot different analytes of different classes. The red filter there happens to be a shorter wavelength, 125 to 160 nanometer filter. The next slide will show you the reason we've got that. You can see on the left, you've got a series of linear alkanes, or these are the paraffins. Their primary absorbance is in that region. And so that's why you'll see linear alkanes pop out if you use a filter that's focused in that region. And just for information, all of the saturated classes have a lot of absorption there. So isoparaffins and naphthenes will also respond well to that filter. And then contrast that with the aromatics over here on the right, and you can see that the main reason that those two filters do what they do. The other thing you can see from these plots is that even though there's a lot of within-class distinction of these spectra, you can also see that the different classes have different regions of prominent absorbance. So, for instance, different classes show different types of features in different regions, and so the different analytes in different classes show different analytes in different classes can easily be distinguished from each other. Aside from using that type of spectral filter, we can also use the full wavelength range characteristics of our spectra, and we do that in two different ways. One is we do a type of fit called a library search. This is basically a shape matching fit. On the top left here, you see a screenshot of our library search. There are two curves on that bottom graph. The blue curve is a spectrum that's recorded from one of our chromatograms. The red curve is the best fit that we got from matching all of the spectra in the library to the best extent possible. After we do this matching, we rank all the analytes according to a fit metric such as the chi-squared or an R-squared metric. So what you're looking at here is the analyte that best fit this absorbance spectrum that we pulled off of the chromatogram. One other thing to point out about this plot, if you look at all the top hits, they're all within the same class. And this is another manifestation of the class distinction character of the VUV spectra. This is a very powerful feature of our spectra, and it greatly simplified the PIONA class type of analysis that I'm going to show you in the second half of the talk. And if you think about it a little bit, what it means is that we don't necessarily have to have all of the reference spectra characterized in order to do classification analysis. So it's a big simplifying step. Second thing that we can do with the full wavelength range spectra is deconvolution. On the bottom right, I'm showing in the dark blue there's the original chromatogram response. And we've gone through and fit each of those regions of interest with a multi-component model that consists of a linear combination of the reference spectra of each of the analytes involved. So peak number 1 is ethylbenzene, peaks number 2 and 3 are M and P xylene. And you can see that the M and P xylene practically co-eluted with each other. After you do this fit, you have those two analytes baseline resolved. And so now you've got those things as though they occurred by themselves. This is probably the most powerful feature of our technology and is the one that is driving our ability to do these gasoline analysis or other complicated samples like this. So all of the prior leads you to, or has led us to two distinct approaches to fuel analysis. The first one is reminiscent of ASTM 6730. And in that, what you do is you make use of exact elution times to the extent possible to define analysis windows. And within those analysis windows, you'll process each peak individually. But because we can do deconvolution, each of these peaks doesn't have to just have a single analyte. It could have 2 or 3 analytes or even more. So since we can do deconvolution, you don't have to baseline separate with the hardware all the things that you would normally have to baseline separate in method 6730 DHA. So basically, the ability to do deconvolution leads to the potential for a faster DHA run. The second methodology makes use of this classification that I stumbled through in the last slide, or last couple of slides. We basically don't try to identify every single analyte, but we try to identify the class of analytes. We divide the chromatogram into a bunch of individual time slices and do kind of a miniature PIONA analysis on each of the time slices. Keep track of the relative weights of all the different analytes that contribute to each of the time slice, and we bucket them, if you will, to keep track of the total amount of response for each of the analytes. And at the end, you can convert that to a mass percent, as is commonly done in ASTM 6839. By the way, when I say that is similar to ASTM 6839, I should qualify that. It's similar information content. The reformulizer method that's described there is actually extremely complex with multiple columns and multiple valves and traps. And we do the whole thing with a single gas chromatograph, a single column, and a single detector. So once again, in addition to being faster, the hardware is significantly less complex. Okay, to illustrate the first method, the detailed hydrocarbon analysis, we've run this Oxy setup blend. This is a purchased standard. It is associated with ASTM 6730. It has about 30 components in it. It also contains several of the key coelutions, and so this serves as kind of a tuning standard. For instance, the benzene methylcyclopentene coelution is there, P-xylene and dimethylheptane. And we can do all of the coelutions in this sample, and so we've run this on just a standard 30-meter column in a relatively fast temperature ramp, and I'll illustrate explicitly one of them, the benzene methylcyclopentene, and then I'll show you the result of repeating that process for all of these groupings. So here is a screenshot of our model and analyze screen. You'll see this when you actually set up a method. When you're actually doing a run in production or something, all of these steps have already been done. So this would all occur in the background. So this is just for illustration purposes. But over there on the upper right, you'll see the original response from the benzene methylcyclopentene elution. And over on the upper left, I set up a model that consists of the benzene reference spectrum and the methylcyclopentene reference spectrum. Those reference spectrum have now popped up on the left-hand side of your screen there. You see the reference spectrum for benzene and that of methyl cyclopentene. You can see that they're completely distinct from each other. Now, just to make a point, the absorbance spectrum shape for a given analyte depends only on what that analyte is. The only thing that the amount does is it changes the scaling. So if I wanted to double the size of that benzene absorbance, I would double the amount of benzene that I'm looking at. Otherwise, the shape stays the same. On the other hand, if you look back over on the right where the response is and pull some of those absorbances out, you'll see that the shape of the absorbance actually does change. And that's because the relative amounts of benzene and methyl cyclopentene are changing. So if you come in and you set up a general linear model that optimizes a scaling factor, benzene and methyl cyclopentene, and the model consists of a linear combination of those two reference spectra, you can fit these absorbance spectra pretty much exactly. And the result at each of those locations is the amount of benzene or methyl cyclopentene, the amount that each of those analytes contributed to the total absorbance that you see there. Then if you carry this a step further and you do that fit over an entire response peak, like I've done here, you get that relative amount at each time point. And the result is a separate chromatogram. You have two new chromatograms, one for each of benzene, one and methyl cyclopentene. Each of those chromatograms is that analyte's contribution to the original total chromatogram. And now you're free to process these peak areas and peak heights, like you see in the list here, as though each of these analytes occurred by themselves. From there, you can put in a calibration value or something, or use a relative response factor to compute mass percent. I haven't done that yet because I haven't told you what our relative response factors are, and that's what we'll do here. And I think this we've chosen a methodology that is pretty similar to what is done in the ASTM methods, 6839 and 6730. We define the relative response factor for methane as 1, and then for any other analyte that's in our library, for which we have a cross-section, we use the total cross-section of the analyte and that of methane to compute a response factor relative to methane. And I think that's a fairly standard thing to do. I'll point out that what we noticed when we first started doing the classification analysis is that within a given class, now the response factors among the various classes are different, but within a different class, as you got above about carbon 5 or so, the response per mass was not that different. And so to keep things simple, we just defined relative response factors that we applied to each of the 5 PIONA classes. This is just a detail because we're going to extend that out later, and I'll show you one of the reasons in just a minute. But we'll probably further break those down at least into different carbon number groupings, kind of like is what's done in 6839. But for now, we've obtained the paraffin relative response factor by the formula that you see there, and the rest were calculated by calibration to a PIONA standard kit. Some of the other analytes were pulled out individually, like oxygenates and a couple of the aromatics, in those cases when we're interested in having those single analyte results. The relative response factors are combined with the determined areas from the actual measurement and deconvolution according to this equation, and that also is fairly standard. And so putting all the things together, all the concepts in the prior slides, and applying that to the entire 30-component chromatogram, and in fact we have 31 components because we discovered we had contaminated the sample. But you can convert all of that into mass percents, and you see that in the mass percent column there. What I did here was I took all of the paraffins, isoparaffins, and so on, and just added up their mass percent results. That's the first column that you see here. I'm comparing that with the values that came from the nominals. And I think overall you can see that the agreement's pretty good. Now this sample, if purchased new and we handled it carefully, would be sufficient, or it would be appropriate for us to use this to actually calibrate relative response factors, and that's probably what we'll do moving forward. For right now, we've just using the generic factors that I described to you, and so they're preliminary. So I think the agreement is pretty good in light of that. And the second thing is, as I mentioned, our standard is kind of old, but you can see that the naphthenes and aromatics could be refined a little bit, and that's probably where that refinement will come from. I've shown a third column over there called VUV-PIONA mass percent. What that is our PIONA code that I'm going to show you in the second half applied to this same sample. It's a very different type of approach, but otherwise uses the same reference spectra and the same response factors. So one of the things that I was looking for, at least from this, was the agreement between our two types of approaches, and you can see that consistency is very good. We can come into these and look at the individual analyte results from the sample. I've plotted mass percent of the nominals on the x-axis, and I've plotted our results on the y-axis. You can see that the correlation is already pretty good just with generic response factors. But we did go ahead and break down the relative response factors by carbon number for the aromatics. And you can see, and for this sample, that basically amounts to giving benzene and toluene their own response factors, and then the higher aromatics a carbon number based one. But you can see that immediately leads to a better correlation. And I think that results like this mean that moving forward we're probably going to further break out our response factors from those 5 classification groups. But we already maintain cross-sections for most of these analytes in our library, and we could, if we wanted to, we could associate a relative response factor to each individual analyte. Okay, to summarize this approach, basically the ability to do deconvolution leads to, if you implement this in a similar way as ASTM 6730, it leads to the ability to do that without having to fully separate everything. And so that means, for instance, there's no need for a pre-column, which is one of the things that the benzene methylcyclopentene grouping is tuned to. And maybe that itself is not such a big deal, but the tuning that goes along with having to use the pre-column, having to optimize that, that could be a big time saving. But certainly the ability to use a shorter column and the ability to do faster temperature ramps are extremely important, and both of those absolutely lead to shorter runs. And so basically very similar to 6730 DHA type analysis, but the potential is a much faster and less complicated type of measurement. Okay, for the second approach, and in fact this was the first that we actually implemented because it's a simpler setup than a DHA type of approach. But I'll start with our 139 component PIONA kit. This is a standard. It consists of 6 samples. 5 of them are background samples, 1 for each of the 5 PIONA classes. And there's 1 sample that combines all of them. And we initially used this kit basically to get reference spectra in our library for all of these different analytes, and enough reference spectra to start with a good class representation. We also use this kit to develop our PIONA mass classification code. So to illustrate how this works, here's a case of coelution. This came from a little bit longer run, one of our preliminary ones. It's not the way that we did the final sample, but it's just for an illustration. But if you zoom into this region between 76 and 77 minutes, you'll see that these two analytes, trimethylbenzene and dimethyl-octane, they at least partially overlap. If you go through the same procedure that I showed you for benzene and methylcyclopentene, you can run through a full deconvolution, you can baseline separate these two analytes, and process them for peak areas. But there's actually a simpler way to do this. Because of the linear nature of the absorbance, if I were to go into the same time window from 76 to 77 minutes, and on a wavelength by wavelength basis, sum up the absorbance to generate a single absorbance spectrum that is the total absorbance of this whole window, and then I fit that absorbance with the same model using the same two analytes. If you set it up correctly, the fit weights are identical to the areas that would have resulted if you had gone through the entire deconvolution process, fitting each and every spectrum. And that may seem like not such an important point, but when you think in terms of automating this process over an entire chromatogram with possibly hundreds of different analytes, it's a big simplifying step. Because if you think about it, it doesn't matter how those responses are arranged within that time window. It doesn't matter if the analytes actually overlap, if they perfectly coalute, or whatever. You can come through and divide your chromatogram into equal time slices and just go through and analyze each time slice one at a time. And keep track of the results and keep adding them to the various class buckets as you go along, according to which class the analytes are in. The only thing that we need to do before proceeding with the full algorithm is figure out what analytes to put into the model for a given time slice. The way that we do that is shown here. We call this a tiered library search approach. Basically what you do is, first of all, you go to a time slice, and if it's the automated algorithm, it's just literally stepping through the chromatogram in order. So you're sitting on a time slice that has a certain width, a few seconds usually. You generate a total absorbance that represents the absorbance for that time slice. Then you implement retention indices, but you use a relatively wide window. So I've mentioned that it's a plus or minus 25 window. And when I say that's relatively wide, that's about halfway between successive linear carbons. So it's nowhere near as restrictive as the use of retention indices in 6730. The main thing that we're doing with this is eliminating the 95 or 98% of the library that couldn't possibly coalute anywhere in the vicinity of your time window. So you've reduced the library to a much smaller subset of analytes that are candidates for elution within the time window that you're looking. Then you perform a library search on that subset, and you store the best result. And it's kind of like one of those first slides that I showed you. It's the same thing, same as a generic library search. Now you've got your best result, and that basically is like assuming a model with a single analyte. Come back and take every pair of analytes from that same list and construct linear combinations of those analyte pairs and fit the total absorbance again, and take the best result from your model that assumes two analytes. That result is significantly better than the one analyte result, then you replace it. If it's not significantly better, you revert back to the single analyte result. And you can repeat for 3 and more analytes. And the idea is that you're looking for the simplest model that explains all of the absorbance that you've collected from that time slice. Result is a prediction for the number of analytes that eluted in the time window, their likely identities, and the weights, the amount that they contributed to the response in that window. And from there, it's a simple matter to look up the class of each analyte and add the weight to the appropriate class. And as you move through the entire chromatogram, you're just building up the total area for each of the PIONA class. Okay, so here's an example run that we did on our 139 component sample. We crammed this one into a little bit less than 16 minutes. We used the 30-meter column and a relatively fast temperature ramp as before. Divided this thing into a whole bunch of time slices. Each one is about 0.03 minutes wide. This shows the first minute where something actually happens. And for instance, if you 1.35 minutes, you have your first analyte coming out, methylbutene. And this is the result of that whole analysis. Form your total absorbance, do the tiered search, and you end up with the best description being 3-methyl-1-butene with a weight of 0.074. And so 0.074 goes into the bucket for olefins. And you can see here that this slice has actually cut this response into a little piece of it falls into the next slice. And in your tiered search, the multi-component model picked up the fact that methylbutene was still there, and also isopentane came in. So added to your olefin bucket is 0.027, and added to your isoparaffin is 0.026. And you just continue that. And really, this is the way that you want to think of the results, and this is the way that we present them actually. For each of these time slices, you're figuring out how much of that response is due to paraffin, isoparaffin, olefin, and so on. And I don't know, you probably didn't catch it, but over at that other end, here you had a case where you've got a linear alkane and then two olefins came out, and those olefin responses were simply summed up before they were added to the olefin bucket. Now, if you go into the weeds in this data and you look closely, you will see that for the most part, the algorithm gets the correct identification or the correct class and the correct weight. If you look at some of the small details, you'll see that there are cases where an analyte was misidentified. In the vast majority of those cases, because of these spectral distinctions, the class was correct. And so for this analysis, that type of error has no effect. There are occasions when an analyte not only is misidentified, it's also misclassified. That is an error. And if you look at those cases and you look at enough of them, you realize that they're actually contributing very, very small components to the total response for these classes, and you realize that you're looking at another component of the measurement error. And that could be stated as the drawback of doing all this. It's a very powerful general method, but due to the non-zero chance of misidentification, you have an extra component to the measurement error that you now have to characterize. And so one way that we've done that is we've taken, and here you see two sets of results. The top table are the compiled areas of each of the 5 classes. The bottom's where we've used relative response factors to convert those to mass percents. And we did multiple runs. And you can see that, and by the way, these runs don't just include fit error. They include injection error. They include the full process of the chromatography. All of those things together come in at less than about 2% relative standard deviation. So we're happy with this result, even though we still want to improve it. And the fit error is certainly an area that we can continue to do that. In order to put it in a context that I think people will be more familiar with, you can look at these mass results. It's the same data, it's just converted to mass percent. This is the absolute error that you see just in terms of mass percent. So it's on the order of 0.1 to 0.3%. Okay, so how does this do if we get a more complicated sample? We were given a PIONA 6 standard. This is basically gasoline, just really well characterized. We did not try to do this on a 16-minute run, but we put it in an under 40-minute run. Still a 30-meter column. It's still a fast temperature ramp. We did beef up the reference library because, well, you have to, because the PIONA kit doesn't include everything that's in gasoline. We needed oxygenates and PAHs and things like that. Otherwise, we didn't adjust the algorithm very much, and we didn't adjust the relative response factors at all. And the reason I'm stressing that is that if you look at the results and compare our results on this top left-hand graph with the total mass percent results reported with the PIONA 6 documentation, you can see we pretty well nailed it. And this was a very good confirmation of implementing the method on a sample where these relative mass percents definitely changed away from the sample that we used to develop the whole thing on, and we're definitely picking those up. You can also go in and look a little more closely at the carbon number breakdown. That's very easy to pull out of our results. And you can see that, and so I've got 5 additional graphs that show that comparison. You can see that we basically got that as well, although if you look at specific areas, you can see regions that where the agreement could be better. I'll mention 2 things here. One is that definitely the relative response factors and breaking them down into at least carbon numbers will probably improve the results a little bit everywhere. The second thing I'll point out is in regards to these naphthenes. When we went and did a similar repeated set of runs, we found that the relative standard deviation was about 2% again for everything except for the naphthenes. It's a little bit higher than that, about 6%. And when we went back and kind of looked at those regions where this happens, we realized that the naphthenes are still underrepresented in the library compared to the other classes. And just to state kind of a general criteria, due to the classification capability, you do not need to have every single analyte characterized in the library, but you do need to have enough of the same class characterized. So if you think of a given class and a given carbon range, you need enough representative spectra in that range in the library so that it serves effectively as a basis set for other unidentified analytes of the same class. And so refining relative response factors and beefing up our library with more representative naphthenes are the next steps that we're going to take, and we anticipate that those will make these results even better. So the advantages to this one, again, the information is very similar to 6839, the reformulizer, but it's nowhere near as complex. It's a GC, a column, and a detector, no valves, and in addition, of course, it's going to be faster just by its nature. One more thing to point out, 6839 calls out some specific oxygenates. We can do the same thing. Basically, what you have to do in that case, if you're interested in a specific compound, make sure that that compound in particular is well represented in the library. You just have a reference spectrum and preferably a cross-section as well to generate its own relative response factor. And we've got that for the primary oxygenates. And you could pull out the BTEX complex as well, the benzene, toluene, ethylbenzene, and xylenes. And so that additional information just comes as a side effect of doing this bulk classification analysis. So to summarize everything, I've shown you 2 approaches to fuel analysis, both approaches you could do with our system, and both approaches really hinge on our ability to do deconvolution, having distinct spectra, especially distinct class spectra in the vacuum ultraviolet region. Either of the methods, whether it be a DHA type or a PIONA type, can be significantly sped up by doing this. And either methodology is significantly less complex, but especially a reformulizer type approach would be made a whole lot simpler. And then going back to the point about the individual analytes, you get this information anyway in doing the 2 analysis that I showed you. So moving forward, we have an eye on combining multiple ASTM methods together to get all of this information in a single run. And that I'm done. Thank you for listening to all of that, and I'll move over to this questions pane and questions. How many compounds are currently in your library? Are you still building it? And can a user add to their own library? The number of compounds currently there are about 600 or so. I think we use maybe 300 in a subset for the PIONA library. We are definitely still building it at a rate of about 50 a month, and users can add their own. And so I think moving forward, we're hoping that there will be a whole lot of sharing as we build up a library that's as extensive as some of these mass spec libraries. But if a customer wants to keep their library proprietary, they can do that as well. How does the analysis deal with response factors given that different species have distinct UV extinction coefficients? This may have been asked before I addressed this, but the way that we generate response factors, if you average the response for these analytes over the entire wavelength region of 125 to 240 nanometers, the per mass response within a class is not much different. And so the primary differentiation is the different classes. And I think I alluded to this several times in the talk. You can easily divide that into response factors for different carbon numbers as well. And basically the way that you do that is you take the cross-section you take reference spectra for representative analytes, you take their cross-sections, you sum them up, and you compare them to the methane cross-section. And there's a simple formula that involves the molecular weights of those two analytes as well. And so you can generate a relative response factor for any analyte. With the carbon number, we're thinking that we are not going to characterize every single analyte or compound that occurs in gasoline. We're planning to divide these response factors further into different carbon numbers. And so what you do in that case is, for instance, with the aromatics, you take all the C10 aromatics that you have, find the relative response factors, and take an average. And that becomes your relative response factor for aromatics of carbon number 10. And I think you saw from the results that in terms of classification and the mass percent, without even taking that step, we're already very close. So it's really just a matter of refinement. By the way, I should point out, and I think I said this earlier, you could define a relative response factor for every single analyte if you wanted. It's bookkeeping, and we already keep fields for that in our software, in our library. In your experience, what is a good rule of thumb of how many compounds can you deconvolve if they coalute? It is easier if they have dramatically different spectral absorbance profiles. That is a correct observation. The ability to do deconvolution depends on how distinct the spectra actually are. The nice thing about the rule of thumb for these analysis, we try to limit it to 3. And that's not necessarily a limit that we've bumped into. As we move forward, we may include 4 or 5. But if you think about it, to the extent that you can do this classification, 4 or 5 should be the most that you'd ever need. We try to enforce 3 coelutions at most using the physical separation still. So that's where we're using the gas chromatograph part and separation, and then use deconvolution to do the rest. So it's definitely still a combination of the 2 technologies, but with a major enabling difference being that we're not limited to a single, or we're not even limited to necessarily 2 analytes. Does the sensitivity increase when the wavelength window is smaller? For this, I might want to go back to spectral filter slide. Very good question. So here's a couple of examples. You can see that here, for instance, with these linear alkanes, you could increase the response, and there are two ways to look at the response too. You don't even have to use an average absorbance. But if you're looking at an integrated response, you could increase the response by decreasing the size of this and focusing only on this region. There's another, and for the aromatics, you could focus only on the maximum. There's a limit to how much you would want to do that. And the reason is that and that's the signal part of the signal to noise. The reason is the noise part, because the noise depends on the lamp intensity. And the lamp intensity is actually best in this region. It's about mediocre here, and it's about average here. So in a region with these aromatics where you have a high signal and a medium level noise, you benefit by decreasing your spectral filter up to a point. You do not want to decrease your spectral filter until you're only looking at the peak of this thing, because then you've reversed the signal to noise gains that you've got. The noise starts to grow faster than your signal does. So there is an optimal filter for signal to noise purposes. That filter depends on the analyte because the response depends on the analyte. Now, one thing that I should point out here, for the types, and all of this is relevant to these two-dimensional chromatograms that we use and show for selectivity. And actually, if you've looked up our paper in analytical chemistry, we did use filters and just traditional response to do the detection limits. For all the analysis I've shown you in this presentation, we've actually used full-range fits to the full spectra. And the nice thing about the full-range fit is that it automatically takes into account the signal-to-noise characteristics throughout the entire region. And so what you end up with is if you do the fit instead of using a specific filter response, you end up with a result that's as good as the best filter that you could pick, basically. So you can either use an optimal filter, which can require some trial and error, or you can use our deconvolution fit. And the deconvolution fit will be about the same quality in terms of detection limits as your optimal filter. Are there any plans to cooperate with ASTM measurement to implement this detector as an official one in ASTM methods? Yes. Difficult to update the library if we need to change the GC brand, and it's not, because the library is part of our software, so you wouldn't have to update anything to do that. Somebody's having a problem with the audio. What's the wavelength range and sample rate of the detector? The full wavelength range of the detector is 115 to 240 nanometers. I've shown you 125 to 240. That's partly because that's the region that's best for this application, and partly for traditional reasons. We used to cut it at 125. The scan rate can be up to 100 hertz. Up to 100 times a second. We typically run it about 5 to 10 scans per second. Are the response factors for C5 plus the same within a class? Roughly speaking, they are, but we'll probably still divide the response factors into carbon number classes moving forward. You do see, as you go below C5, you can start to see definitely more dependence on the carbon numbers. So if you're working with analytes that are light, you're going to want to go with analyte-specific or carbon number-based response factors. What is the sensitivity of the detector? Could you provide a compound? Could you provide an example? Again, a good place to start is with our analytical chemistry paper, because we published several just basic figures of merit there. Our detection limits range in terms of mass from the tens of picograms to the hundreds of picograms. To sort of rank the analytes that are in gasoline, these hydrocarbons like aromatics and linear alkanes are going to be in the low to mid tens of picograms, and oxygenates like methanol are going to be on the higher end. They're going to be in the hundreds of picograms. And as a concentration example, maybe the common one is to sort of translate that mass to an effective parts per billion. And so for a 1 microliter splitless injection of a density 1 sample, that's equivalent to tens to hundreds of parts per billion. I'll point out that that's on these runs that I've been showing you, these have been very low injection volumes and very high split ratios. And one of the reasons is that you're much more concerned with separation and things like that. All of the compounds that I looked at in these two applications are in the percent level or tenths or decimal percent levels. And so they're nowhere near those detection limits. And with the low injection volume and the high split ratio, I'll point out that if there are special cases, such as for particular analytes that are close to the detection limits, there's plenty of room to reduce the split ratio or increase the injection volume to accommodate that. But since it's not really a detection limit dependent problem, I haven't really bothered to calculate detection limits for the particular methods that I've shown here. Does the software have a choice to optimize the ratio of analytes during the linear model, or is it up to the user to decide? In the sort of building the method by hand that I showed you with the DHA approach, that is up to the user during the setup phase. And so we're in the way that works in practice, once you have those methods set up, you can store those the entire thing as an analysis method, and once a new sample is run, the same analysis is done on the same time windows using the same fit method components. So what really happens there is that the setup becomes kind of a pain, which is why I don't have full results using the DHA approach yet, but that setup should only have to be done and optimized one time. So it's kind of similar to the 6730, which must have undergone something similar or even more involved during the setup. Once you have a method specified that uses a particular column and things like that, then you don't have to go back and set those analyses up anymore. I'll also point out that you have a lot of leeway if you're changing just general GC conditions by using retention indices. That's still a good place to use those, but all you have to do in those cases is call out a few specific compounds. And for instance, these aromatics, for us, are very distinctive. And you don't really need any special automation to go through and spot benzene, or to mention a few others, ethanol or methyl naphthalene, just to kind of cover the whole range. If you went through and found those first and just adjusted their retention times, you can adjust the entire chromatogram. For the second type of analysis, it's pretty much fully automated. The retention index used there is a pretty wide window, and at each time step that you're in the chromatogram, retention indices are used to reduce the list to a great extent. But within that list, the software automatically finds those analytes for you. So there's no real concept of setting up an analysis in each window in that case. That method is very easy to implement with new temperature ramps or with a new length of column. And as long as you don't mix up all the retention orders or something like that. Typically, I've just gone through by hand and updated a handful of analytes, and that pretty much updates everything. Moving forward, we'll build in an automated means to do. Thinking it, if you think it a little bit further, you could imagine an easy way to combine those two concepts when you're actually setting up a DHA type of method, because you could do a tiered search on the window that you're currently working with. There's nothing that says it can't be manual. And that we're anticipating implementing that as well as a way to assist people to where you don't have to have so much knowledge about what's there. You can once again eliminate most of the library that couldn't possibly be there, and then do a tiered search process to get a good estimate of what the analyte should be there. Nevertheless, with the DHA approach, we probably lock it down at that point, because that's part of the point with that approach, is that within each analysis window, you're doing a very specific analysis. Okay, I'm gonna try to do one more question here. Okay, I'll do two more because someone's asked what the price range is, and you should contact contact our sales office for that. How long does it take to process data for a PIONA 6 run? Does any integration similar to GC analysis involved? And how extended is the library? Gasoline has more than 400 components. And yes, we did look at a PIONA 6 sample that did have more than 400 components. I think I mentioned earlier that our PIONA library has somewhere around 300. There's a lot of overlap because of the classification. And just to put that in a little more context, we beefed up our library actually making use of some of these gasoline production streams. And so not only do we not have every single compound specifically identified, some of them are identified simply by class. And in that PIONA analysis, that's what we're trying to do for the vast majority of these compounds, is determine what's the class that it's in and what's its contribution to the total response. And because of this class distinction, and luckily I'm sitting here right on that slide, because of these class distinctions, you can do this. You don't have to have all of the components accurately characterized in order to get a good bulk mass percent classification of these things. Any integration similar to GC analysis? If I'm interpreting that question right, I think the answer is no. This is a fully automated process. And to answer the question about how long it takes, maybe 5 minutes on my slow laptop. That's something that we haven't even bothered to optimize. But, here's a piece of information for you. In this tiered library search, that involves a whole lot of fits from which you're throwing away a lot of the poorer results. Those fits occur at a rate of several hundred per second. So that until you build up to 4 and 5 simultaneous, what really takes all the time is putting together all the different combinations from your list. And until you get up to 4 or 5 or more, you're not looking at a whole lot of time per time slice. Certainly, it's the data processing is much, much faster than the actual run. So in a production environment, it all happens practically real time, but of course, the conversion to mass percent step, of course, has to wait for the end. But you could process all the rest of it while the run's going on. I think with that, stop, and I appreciate you hanging out with me for, looks like, a full hour at this point. Thanks for attending the webinar, and we'll try to get to any of these questions that I didn't get to with some follow-up emails or something like that. Thank you very much.